So this lecture, two goals. The first one is to understand how to basically interpret what's going on in a detector. So the noise in the detector and some of the hype about recent detectors. You saw the K2 detector yesterday, and it was working beautifully at incredibly high energy losses and doing much, much better than the old-fashioned scintillator CCD detectors. It's not a noise-free detector, but it's pretty darn good. There are other designs of detectors. I want to give you a flavor of some of the trade-offs in how you design these things, because there's a lot that's happening with detector development right now. And then I'm going to talk about our pixel array detector and the physics that you can do with that, because you're going to play with that on the afternoon. And essentially what the physics the pixel array detector is doing is it's doing a complete phase space measurement. It's measuring both momentum and position simultaneously. And another way to put that is it's recording a hell of a lot of diffraction patterns. Okay. So the first thing, and if there's nothing else you remember from this lecture, this discussion of noise, I'll point out the formula I want you to remember and not forget. But obviously, I can't form an image unless I put a whole bunch of electrons on the image, right? So at very low doses, images don't look like much. And that's the whole discussion of dose and resolution, is I can't resolve features unless I have enough electrons to do that. Albert Rose here, has written a number of classic books. Basically, he worked for RCA, which used to make TVs, and he basically would make noisy enough images and ask people when they could see the image on the TV set and when they got annoyed by the image. So what was an image that people were happy looking at, and what was an image that they just couldn't figure out what was going on. And his criteria was basically, for each pixel, you want a signal-to-noise ratio of about bigger than 5, was the rough rule of thumb. Or another way to look at it is signal-to-noise ratio of 5 is about 20% contrast. It depends on the size of the object and the shape of the object, but that's sort of the rough rule of thumb that we use when we're trying to determine if I have to plug numbers into a calculation and work out whether I'm going to be able to see things or not. That's our order of magnitude rough rule of thumb number. Now, the noise that we're interested in is essentially a counting noise, because it's 1 electron shows up, or 2 electrons show up, or 3 electrons show up. And that noise is called Poisson noise, or counting or shot noise. All of it's the same thing. And the reason why it's Poisson noise is it follows Poisson statistics. And Poisson statistics is the probability distribution given by this formula over here. And the probability distribution is what is the probability of measuring k counts for a signal that has a mean of n. So my signal is on average n electrons per second. What is the probability that I measure not 1 electron per second, but 2 electrons per second, or half an electron per second, or in fact no electrons per second? And it follows this distribution curve over here. That's the formula. And then I've plotted it out here for a mean of 1. So this is a information channel where I'm supposed to have 1 electron per pixel. And in fact, on average, I do get 1 electron per pixel. But I also often get more than 1 electron per pixel, sometimes 5 electrons, and sometimes even 10 electrons. The thing about this distribution, it's different. Normally, you're used to seeing Gaussian distributions, right? And the Gaussian is it has a mean and it has a standard deviation. So if I kind of plotted them up, my Gaussian probability of finding something, you know, it has a mean of mu, and it has a standard deviation of sigma. You're used to seeing that distribution. And 2/3 of the time, my signal will fall between plus or minus sigma. And 95% of the time, it will fall between plus or minus 2 sigma. The Poisson distribution is kind of a little bit more asymmetric. It does that. And the mean of the Poisson distribution is basically going to be n, and the standard deviation is square root of n. So the Poisson distribution, it doesn't have two free parameters. It only has one parameter, which is n. And then this is the rule of thumb I want you to remember. If I have n counts per channel, the uncertainty or the likelihood that I actually measure n counts is actually, the spread is square root of n, right? Standard deviation is square root of n. So here's an example. Obviously, signal-to-noise ratio is n over square root of n is square root of n. So this is very useful as a formula. Rose's criteria, Rose said, I want a signal-to-noise ratio of 5. That means I need at least 25 electrons per pixel to get a nice looking image. And if it doesn't look good, I need more pixels, and kind of the eye will average them out. And that 25 number will pop up a bit because Gatan was careful to at least let you do that on their detector. So let's take an example. Here's some Poisson noise. My mean is n. My standard deviation is square root of n. So imagine I am trying to count, and I'm only expecting 1 electron per pixel. And I take a line profile for an image where on average there's 1 electron per pixel. This is what that distribution will look like. Right? N equals 1. A lot of channels have 0 in them. Some of them actually go up to n equals 5. Square root of n is plus or minus 1. 2/3 of my counts should be between plus and minus 1, and that looks to be about right. You know, I've got 10 values here, and about 3 of them are outside that range. So that's all good. So this is perfectly reasonable. The problem is, when you're doing things like EDX mapping, you get very, 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 very few counts. And so what happens is your EDX map line profile might look like this. The EDX software is very, 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 very naughty, and it will try to smooth this all out and make it look nice and smooth, and then you'll see all these big blobby features, and you'd go, oh, look, in EDX I detected a nice atom here and another atom there, and there's another atom cluster over here, and there's no material in between. And that's just all noise, and so you should never let the EDX software smooth your data. You should look at the raw counts, and you should inspect their numbers and understand whether the statistics are outside that square root of n range. That in this case, this is not a bunch of atoms, this is random noise. I cannot tell you how many times my materials microscopy colleagues have made this mistake because they didn't know about square root of n. Now, you actually need a lot of electrons before things start looking smooth. 10 electrons, it's still pretty bumpy. 100 electrons, square root of n is a 10% variation. It's looking a little bit better now. And 1,000 electrons is a 3% variation. It's still not flat. But it's still looking pretty good, right? You can tell that this is a uniform distribution, whereas you couldn't really figure that out from that there. So the problem with this is the noise, right, is scaling like square root of n. So if I want to improve my noise by a factor of 10, I've got to collect 100 times more data. That's hard. So at some point, you just need a better, electron microscope with more electrons in it, because you can't get around this Poisson noise. This is intrinsic to the process of just producing electrons, right? Electrons come out randomly. If you don't have enough electrons, you're going to have noise. No matter how good your detector is, you're still in trouble. So this is a fundamental limit, and if you don't have enough electrons to begin with, nothing can save you. Given that fundamental limit, we can go back to the very first picture I showed you, and you can ask the question, well, how many electrons do I need to resolve a particular feature of a different size? And I apply that Poisson noise square root of n analysis along with the collection efficiency of my detection mode, right? Bright field is maybe 10% efficient, and Annular dark field is 1%, and EELS is maybe 0.1%. And then you can work out how much dose I have to apply to a sample to get a particular resolution. And this is for elastic imaging modes. It depends on the contrast that you need. And you can kind of plug some numbers in. And typically, for typical elastic imaging modes, if I want to do atomic resolution, I need like 10 to the 4 to 10 to the 5 electrons per square nanometer. Biologists will tell you that that's way too many. And so when I look at things that are like polymers, maybe my resolution is down to a nanometer, because if I want more than a nanometer, I need 1,000 electrons per square nanometer, and that's above the radiation damage threshold for an organic material. And so then you've got to be clever. You've either got to go to cryo so that you can take more dose, or you have to do very clever signal averaging from different particles. But this is a fundamental limit, and you can't really get around it. Now, the next thing is, once I've kept an idea, and I know what my incoming signal to noise is, I know what my incoming noise is, I know what my incoming signal would look like for an ideal detector, what can a detector do for us? And the way we characterize detectors is in terms of a number. There's several metrics, but the popular one is the detective quantum efficiency, or DQE. You'll hear that thrown around a lot. It's the jargon over here. And for Poisson, if the incident noise source is following Poisson statistics, then the detective quantum efficiency is basically, it's a measure of how much worse did I make the signal-to-noise ratio. What's important is the image came in with a bunch of noise because it had Poisson statistics. And the only thing the detector can do is it can either pass it through perfectly or it can make it noisier. It can't make it better, because to make it better, I'd have to add information that didn't exist. And if my DQE got bigger than 1, and I measured that, that would mean there was some horrible smoothing going on in the detector. And that can happen if you've got too much smoothing. So the DQE, which is the output signal-to-noise ratio, ratio to input signal ratio, and we do it squared because it's a power measurement rather than an amplitude measurement, has to be less than 1. And 1 means it's an ideal detector and did not add noise. Anything less than 1 means you added noise. So here's just a quick numerical example of, I have a detector that, a typical detector would be like a scintillator and a CCD camera. So the scintillator takes 1 electron in, and that 1 electron goes through the scintillator and generates a huge number of electron hole pairs that recombine and emit multiple photons. So a scintillator has a gain that takes an incident quantum, which is 1 electron, and an output quanta, which are photons, and it takes 1 incident electron and might put out 10 or 100 or 1,000 photons. Right? And a good scintillator, if I have a 100 kilovolt electron and I have a 3 eV band gap, then maybe I'm going to get out 30,000 electron hole pairs. Maybe 1% of those will be converted to photons. The rest will decay thermally. And then my conversion is, effectively for the scintillator, maybe 30 photons. And my detector, the CCD camera, can detect a single photon. So it detects 30 things. So it has a gain of 30 in terms of quanta. If I had n incident electrons, my incident signal-to-noise ratio is square root of n. My input noise was square root of n. That fluctuation is converted to square root of n times the gain, because it's those n electron square root of n fluctuation got turned into square root of n times g photons. The output signal is g times n. And then the variance in the output is, that's the number of photons coming out, is gn photons. The noise in the number of photons is square root of this thing, which is square root of gn, right? The thing I want you to remember at the end of this lecture and tomorrow, and if I call you up in the middle of the night and I say, if I have n photons, what's the noise? You'll say square root of n. And you'll know to write down plus or minus square root of n as the variations. So I have now 2 output noise sources. I have square root of n, which is the number of fluctuations in the photons, and I had the number of fluctuations in the incident electrons. They're independent sources. I add them in quadrature. The output noise is the square of these two objects. I now calculate my output signal to noise ratio, and then the DQE is input signal to noise, output signal to noise. The DQE of a scintillator with a gain of G is 1 over 1 plus 1 over G. And this immediately tells me if I want the DQE of the scintillator to be high, it has to generate a lot of photons. And that often means a high beam energy. So scintillators work well for high voltages, which is all of TEM. They don't work as well for SEM, where you might only be getting 5 or 6 photons out for each incident electron. But they're pretty good for TEM. So a lot of our CCD cameras use scintillators, and you need to make sure that you have a high conversion efficiency. The direct detectors like the K2 that you played on and our pixel array detector, the gain factor there is the number of electron hole pairs, and those number of electron hole pairs, it's usually like 30,000 electron hole pairs per incident electron. And so this thing, G, is so big that the DQE, in terms of this gain stage, is effectively 1. But there are other noise sources we're going to look at as well. So if I have a scintillator plus CCD, the paper that analyzes this very nicely is this paper by Andrei Kravanek back when he was at Gatan. And this was to build an early EELS system. And what he's showing you over here is the problems with the CCD camera, and Paolo put up a slide on this one, is I don't just have fluctuations in the gain to give me a noise source. I have a readout noise. Every time I read out, my analog to digital converter introduces noise. And I just have a thermal noise as a background in the detector, that my analog electronics has thermal noise that produces noise, and I add up my thermal noise term, my readout noise term, and the fact that my scintillator is not uniform, it has channel-to-channel gain variations. And then what you now realize is that my DQE is very, very poor on this particular detector. This is an ancient detector from before you were born. And it had just a huge amount of thermal noise in it. And so it had practically no DQE. It couldn't detect a single electron very effectively. But if you dumped a whole bunch of electrons on the detector, the signal was huge compared to the dark noise. And then as long as you didn't have too many channel-to-channel gain variations, the DQE could look pretty good. He's left a couple of factors off, so the DQE was never as high as 1. But he's just analyzing those noise sources. A modern detector does much better than this. This is sort of numbers that I got basically from effectively this is what our neon would look like based on its noise performance. So this is a scintillator plus CCD for a modern camera. It does really well at large count rates, so a couple of hundred to a couple of thousand electrons per pixel per readout range. Looks good. It has single electron sensitivity, but it does add a lot of noise to the detector at very low count rates. This is a tenth of 1 electron every 10 pixels, which is not a lot of stuff. So at that point, the dark noise dominates. So it's not so good. But the detector works nicely when you've got 10 to 60,000 electrons per pixel. And then over here, what's happening is each pixel, the scintillator has variations, the CCD has variations. There are channel-to-channel gain variations, and eventually those dominate because you can't correct for them perfectly. And so now the DQE falls off at ridiculously high rates. What I really should have marked in over here is over here the detector is probably totally saturated. So you're not going to be upset that that's down there because you've already burned a hole in the scintillator by the time you did that. So the lesson is the modern CCDs are really, really good for very intense beams, but they're not that great at very, very low count rates. So if you're a biologist, and a biologist can only put a couple of electrons per square angstrom on a sample, you're going to be very unhappy down there. Biologist is going to work over there, or maybe even down there, and you're not going to be very happy. On the other hand, the K2 camera that you got to play with yesterday its DQE versus dose looks something like this, right? It's absolutely phenomenal at the low count rates, and then when it gets to the higher count rates, well, it kind of gives up. It just chokes. It can't handle that many electrons pouring into it that quickly. But at that point, you don't care because you've got a perfectly good CCD camera that works there anyhow. So that kind of tells you where the K2 does a wonderful job is when I don't have a lot of electrons per channel. And it just fills in a nice gap that the other technologies can't do. So, you know, the strategies on the CCD camera, if I have a low count rate, I don't want to do a lot of readouts because multiple readouts adds readout noise. At high count rates, I need a very, very good gain normalization, but I can do multiple readouts and I can actually shift around to average out gain normalization things if I have to push that up a little bit. So that's sort of the general space of DQE. The K2 is a little complicated in how we deal with DQE. And that is got to do with two things. The first is the nature of pulse counting, and the second is the design, the physical design of the detector. So the first problem is let's talk a little bit about pulse counting. So if I took the output of my detector and I just histogrammed, so what happens is my detector, first stage of the detector is it does an analog readout of whatever's on each pixel. So there's an analog little transistor, an amplifier that's going to read out the electrons. It's going to convert it to some voltage, and then you're going to digitize the voltage. So if you were to histogram the output signal, output level, and number of pixels that, or number of levels that had that intensity, a histogram would have one peak over here. This is the thermal noise, and that would be present whether or not you had a signal on the detector or not. This is just the dark noise in the detector, which is just thermal recombination because I'm exciting electron hole pairs from the valence band to the conduction band. The second thing that you want is the signal generated by an electron. And that might be something that looks like this. This is just a generic output of a generic detector. Now, what pulse counting does is I know that each electron produces a pulse that will be somewhere in this envelope over here, right? A particular electron might have this shape. One electron will hit my piece of silicon. It'll generate 20,000 electron hole pairs. There'll be an energy distribution to it. It'll fall somewhere in this range over here. They don't all have the same energy. What pulse counting does is you say anything that has an output level bigger than my threshold of my discriminator, I'm going to call an electron. And anything that has a threshold less than the level of this discriminator, I'm going to call nothing, 0. And so what will happen is if I had a little peak that showed up like as a function of time, there's a whole bunch of noise, there's a little sharp peak like that, there's more noise, and my discriminator level is set there, the output is going to be 1 and 0s everywhere else. And the beauty of this setup is if most of the time you've got noise, if I integrated and summed up this signal, 90% of that would just be the noise down there. And that's the dark noise that was killing my DQE in the previous plot. So the beauty of the pulse counting is I've thresholded and I've thrown away the noise. The problem is when I do this, the signal out, right? So signal out is the signal in, which times an efficiency factor, because there's always a tail at low energy. So there are always going to be some some electrons that just didn't generate a big enough energy that you could count them. So signal out times, say, a 1 minus sigma factor, and that's the little piece that you're missing. And if you think about it, so this is equal to 1 minus sigma times n. Remember, the dQe is proportional to the signal-to-noise ratio on the output squared, which means it's proportional to 1 minus sigma squared. So the fact that I'm missing counts directly reduces your dQe. There's a second problem. There's this little bit of a tail over here, which is the noise that managed to sneak in. And so here's some random noise. If my discriminator is just a little bit lower down, this might be a piece of random thermal noise that I'm going to miscount as an electron. So my noise term, you actually get to add a noise term in the noise part of your denominator of the thing. So it looks like there's a noise term and you can write it down. It's just basically dark noise times some fraction, which is the tail above that discriminator. So the noise out, there'll be a, the noise out is going to be square root of n, which is the counts that you got, squared plus thermal noise times some fraction of the thermal noise. And that too impacts the signal at low count rates. So now if I'm at very low count rates, eventually I'm going to miscount this piece. This one tends not to be a big deal because it's actually quite small. It's there, but you'll only notice it if you're trying to run your K2 as a pixel array detector, because then I'm summing over tens of thousands of pixels, and then these tails add up and mess me up. But the big one that decreases the dQe of the K2 is the fact that I'm missing the low energy tail of the pulse. And that knocks the dQe down by about 20%. And that brings me to the second part of what goes on with the K2. I'm going to touch on this again later, but the K2 is what's called a transmission detector. It also has the acronym of MAPS, monolithic active pixel sensor. So what the K2 is, it's a piece of silicon, and that piece of silicon has the pixel, which is this little thing up over here, and all of the electronics built into it on the same chip. And the trick is, the idea is that the electron beam goes into the silicon. We know the electron beam is going to spread like crazy in the silicon. So the trick is the active region of the sensor is very, very thin, and so the beam doesn't get to spread much in the sensor. And this means that the pixels in the K2 can be like 5 microns in size, and you still get really, really, really good point spread functions. But most of the energy deposited by the beam is dumped into silicon below the detector. Some of it will backscatter and maybe hit another pixel, and so occasionally another pixel will light up by mistake. That's relatively rare because backscattering is rare. And if you're smart and you can back-thin the detector, this gets even better. The problem is, because only a very small fraction of energy is deposited in this thin layer, it's about a few kilovolts out of 200 to 300 keV, the energy distribution is what's called a Landau distribution. It's an unbounded distribution with a very, very long tail to it. This is what it looks like in an early version of the K2. So this is a 200 kilovolt electron, and the bottom line here, if this wasn't displaying and being annoying, for whatever reason that it is, there we go. This is the energy deposited in the detector measured by the number of electron hole pairs that was generated in the detector. So what you can see is the 200 keV electron produces little, this is a histogram. Sometimes it produces a pulse of 5 keV in energy, sometimes it produces a 15 keV energy pulse. If you drop the beam of the energy of the electron beam, you'll probably dump more energy into the detector, and if you pushed up the beam energy, you'd put less energy into the detector, because most of it's being transmitted. So now you ask yourself, what does the noise in the detector looks like? and here is the noise in the detector. And you can see that there's a very nice separation between the noise peak and the detected electron peak. So this is a good candidate for pulse counting, because I just have to put my threshold somewhere in this region over here, and then I can reject almost all of the noise, and I can keep almost all of the signal. So that's what you really want to see on a good detector. The problem is if I look a little more carefully down here, there is in fact a bit of overlap, and that's why the DQE is not 1, is because I can't separate those two regions out cleanly. But you can look at this thing and see that most of the time, in terms of areas under those curves, it's going to do a pretty darn good job. So where you run into trouble is, imagine I had, I have 4,000 by 4,000 pixels, and I want to do a CCD diffraction pattern, so I bin them up by 100 by 100. So now that's 10,000 channels. That tail will give you 1 out of 10,000 wrong, and now I've lost single electron sensitivity. So this detector was designed for biological imaging. It wasn't designed for diffraction. It does a great job for biological imaging, but if I've got an image that's very, very sparse, this little overlap tail is still going to cause me a problem. Okay, so there's my threshold. The effect of pulse counting is if the threshold is too low, I count noise by mistake. The threshold is too high, I miscount. Both of these effects reduce the DQE, and that means my DQE is not 1, but it's somewhere more below 1, maybe 0.8, 0.9, which is still pretty good. CCD cameras are like 0.6, sometimes 0.8 if you're lucky. So here's a slightly more subtle comparison of this thing. So what I'm looking at here is DQE as a function of spatial frequency. So what this is measuring, DQE at 0 is what we've been talking about before, DQE of a single pixel, right? But this is now measuring the DQE as a function of spatial frequency. So this is allowing for the possibility that there's blurring in the detector. An ideal detector, you might hope for a DQE of 1 at all frequencies, but there is a point spread function to things. Simply, even the very fact that your pixel is a finite size means your DQE can't be 1 at every spatial frequency. The fact that the pixel is a finite size means you don't know where in that pixel the particle fell, and that means if I just had an ideal detector with no noise in it, the DQE would be Fourier transform, because this is a spatial frequency, of a step function, which is a sinc function, and the ideal DQE would start at 1 and would go down to about there. So we look over here, and you look at film, which is what biologists used to use until a few years ago. Film has a horrible DQE. Here are a couple of other direct electron systems. None of them have an ideal DQE, and none of them actually match the ideal curve either. But you can see the K2, which is the detector we got, is doing pretty nicely. 0.8 is close to 1. And over there, OK, it's dropped off. But usually you worry about DQE at half Nyquist, which is about there. So it's not bad, and it looks pretty good. Now, I said this was at low dose rate. And that's because the way these detectors are working is they're counting individual electron pulses. So what they're doing is you have electronics that when this detector picks up an edge that goes high, it adds 1 to the counter, and then it tries to get rid of the charge in the silicon. And the problem is, what happens if another electron arrives over there in the same time interval where we haven't been able to get the electrons out of the silicon because of the capacitance of the system? And in fact, just simply, if I fire an electron into a piece of silicon and it produces a huge number of electron hole pairs, I can't pull it out of the silicon very quickly. It takes about a microsecond to get out of the silicon. So then the problem is, if I have too many electrons showing up because my electronics is slow, then I count the first electron over here, but I miss the second electron. So what you see is I put in an input dose over here, and then if the detector was perfectly linear, it would follow the straight line, and this would be a DQE of 1. If I'm missing electrons, then my DQE is going to drop. because I missed counts. And what's happening over here is if I just do Poisson statistics and ask what's the probability that 2 electrons arrive in the same interval or 3 electrons arrive in the same interval, and I miss that second and third electron, that number, that probability goes up as the dose rate goes up. So you can just do the math, and this is the correction factor. And what you'll find is that if I have a K2 running at 10 electrons per second per pixel, my DQE is down by about 14%. So I started at 85%, and at 10 electrons per second, I'm down to about 70% DQE. And here's a measurement of exactly that happening. And you can see the asymptotic limit at very, very low count rates will be a DQE of 0.85. And the previous measurement here gave a DQE of 0.8, and that's because they were sort of measuring probably at a count rate about there. So important thing to remember about pulse counting is great as long as you have nothing to count. And the efficiency goes down as counts start ending up on the detector. So when you're thinking about designing detectors, I talked about this blurring as a function of spatial frequency. What's going on here is that I fire an electron into a piece of silicon, and the electron is going to spread out. And if the electron spreads out so much that it hits a neighboring pixel, then you've got a blurring function that is more than 1 pixel, and therefore your point spread function is reduced, and your MTF is blurred out, and your DQE goes down. So when we're designing detectors, we want to make sure that we don't have too much stuff ending up in neighboring pixels. So our detector, the EM pad, has 150 micron wide pixels, which means that most of the time our 50% diameter fits inside a pixel, and there's going to be very, very little blurring. The things like the K2 is they design very, very thin pixels, and so you have less blurring to worry about. The problem is with the very thin pixel, you're not collecting all of the electrons, and that adds to the noise and the sense that reduces the sensitivity of the detector. So that's the trade-off you make. And then there's a couple of stupid things you can do, which neither us nor Gatan do, but Medipix and PN Sensor do, which is they make very thick pixels because they were designed for X-rays, not for electrons, and then they make very narrow pixels like that. This is a complete disaster. Having a narrow pixel that is very, very deep absolutely guarantees your point spread function is going to totally fail you, because most of the electrons end up outside your pixel. That makes pulse counting impossible, or at least. So what happens is when you look at the Medipix, it works great at low beam voltages where it hasn't spread outside the pixel, but it misbehaves very badly at high voltages because it's missing all the stuff outside the pixel. So we gave up, you can have lots of pixels that are small, but you have a huge blurring on each pixel, which just means you're collecting extra data for no good reason. So we just said, I'm just going to have large pixels, then I don't have to worry about data. So this is the point spread function at 80 kilovolts as a function of pixel size. So you can see that at 150 micron pixel, the transfer function is almost ideal. It just doesn't blur. On the other hand, if I have a 50 micron pixel at 80 kilovolts, I've already taken a 40% hit in performance. And I go to 200 kilovolts, and there's practically no information that I'm able to collect from a 50 micron pixel. So all you did was you made more pixels, and then you couldn't use them at all because they just blurred out. So here's just, this is our detector, the EM pad you're going to work on this afternoon, showing the point spread function at different beam voltages. At 80 kilovolts, it's almost 1 pixel. This is just occasionally you end up on the boundary of 2 pixels. The beam is much smaller than a pixel, but on average, because the beam is about 20 microns and the pixel is 150 microns, every now and then you'll end up on the boundary of 2 pixels, and then you got that little tail on the side. MTF is pretty good. It's close to ideal at 80 kilovolts. At 300 kilovolts, there's a little bit more blurring going on. The other detectors just can't even work at those voltages. So, you know, we sometimes say, well, that looks blurry, and they say it's blurry, but it still works. The other one is the full width, the 100th maximum, which is what you need for diffraction work, is very, very tiny because the electrons don't get to travel a long distance in silicon. Okay, so if we take a look at performance of these different detectors based on the size of the pixels, the DQE of the EM pad is extremely high at all beam voltages. The pulse counting detectors with tiny pixels have a DQE that drops as beam voltage goes up because the beam gets spread over multiple pixels. And it's not really clear these things work properly at the high voltages. The K2 is not really fair to compare on this plot because it's designed for something very different, but it has a pretty good DQE and a pretty good Nyquist DQE as well. The next thing you have to worry about is how these detectors perform. So here's our detector. You can kind of see this is the peak from a single electron. There's a peak from 2 electrons, and it works at all beam voltages. So one of the things you want to watch out for with these detectors is if you're pulse counting, you can't count a lot of electrons. And that means you can't put a lot of electrons on the detector. So here's the PNCCD. This is their advertising brochure. And they're showing a well depth that can handle 18 electrons per pixel. So this is what your diffraction patterns look like in one frame. And if you want a nice diffraction pattern, you have to take 500 frames, which takes half a second, which is very slow. If you have a good dynamic range, which is what our detector is designed to do, and I'll explain in a minute how that works, then these are what the diffraction patterns look like in one frame. You've got all the details in the central disk, a little bit better than that, and you have all the details in the tail, which is what he was trying to get over there. And then if I average up 10 frames, I'm already looking nicer than this one, and 100 frames, it's pretty much the same as 10 frames. I can do in 10 milliseconds what they can do in 500 milliseconds. And maybe I would argue in 1 millisecond the detail, because this is on a log scale and that one's a linear scale. So let's revisit the question now of dark field image of graphene. Right? So we talked about this morning. What I wanted to do was I wanted to take a diffraction pattern and then put a tiny aperture in and then use that to produce an image where every color is a different piece of angular scattering. Right? So what I've effectively done is I have built up a data cube where I have a huge amount of diffraction information and I have real space information at the same time. The problem is, to do this, I had to take multiple images. If I wanted to have an image where at every point in the image I could tell you what the diffraction pattern was, and I did it by TEM, I would have to move this aperture around everywhere in this diffraction pattern. I'd have to take thousands of images. It would be very dose inefficient, and it would take a very long time to do. So I want to do this experiment backwards. What I want to do is I want to be able to scan the beam and record a diffraction pattern at every point in real space, and then I can reproduce this information again, but having done it by reciprocity. Remember, we can flip everything upside down. So here's the idea. I take my electron beam, I make it reasonably parallel, but not too parallel. Remember what I told you with this imaging, the resolution is set by the size of this aperture. So what I'm going to do is I'm going to make a beam where before the sample I've set an aperture, which is basically my probe-forming aperture, which is going to basically be this thing. And that's going to give me a diffraction spot that is that wide. Right? So I now look at this beam, and I've illuminated that range of angles. There's my diffraction. This is a monolayer of tungsten sulfide. There's my diffraction spot. So this aperture size is about 1/5 of the diffraction spacing. So I'm expecting a resolution of about 5 atoms. So, and that's delta K, delta X. And now this is a diffraction pattern from a single spot. So I now want to scan my beam around and record a diffraction pattern at every point in the image. If I do that, this is what you're going to do this afternoon, and I just look at the intensity in the central spot, that would give me the same thing that would be equivalent to a bright field TM image. If I look at the intensity integrated in one of these diffraction spots, that would be the same as having done one of those dark field images where I had simply selected one aperture over there, and then all the electrons that scattered at that angle showed up. Now I've done that same experiment in STEM mode by looking at the integrated intensity of that diffraction spot there. If I pick a different diffraction spot, I get a different piece of information. In order to do that, I obviously need a very fast detector. This EM pad detector we're going to look at this afternoon reads out very quickly, so you don't have to wait a long time to record your diffraction patterns. It has a single electron sensitivity where the noise is less than 1/100th of an electron, so you don't have to worry about it. And you can threshold it away if you want to, which would give you effectively pulse counting mode. Most of the time we just don't worry about it too much. And then the dynamic range lets me record one electron out there or all the electrons in the central beam. I don't have to put a beam stop in to stop that beam from saturating. And for some of the more sophisticated imaging modes, that's going to be very important. So the detector is described in this paper over here. The NC State guys are supposed to be getting a copy of this detector that FEI is building. Actually, we built it for them, and they're trying to put it in a nice case. And they keep building the wrong case, so it'll show up, but maybe, you know, not as soon as you thought. But certainly, hopefully by next year it'll be there. Anyhow, you know, if you want to talk about the detector, all the technical details are in here. I'm going to talk about a few of those technical details next. The idea of using these diffraction patterns and one of these kind of detectors to get diffraction information, we started working on this about a decade ago. Our first detector was 16 by 16 pixels, and it didn't have enough dynamic range, but it worked on our baby microscope, and we used the center of mass to calculate grain orientation. I'll come back to this, but basically what we're doing was, remember when this morning we saw those diffraction patterns with the tilted Avold sphere that had little rings on them? Well, if I measure where the average center of the diffraction pattern is, it's sensitive to the tilt of the Avold sphere. And so that's all we've done over here, is we've averaged the diffraction pattern, got the center of mass, and it's told us the grain contrast. So this was kind of the first time center of mass imaging was actually ever done, about a decade ago, and then we went back and worked on building a better detector with more dynamic range, because electrons are big. Now, why do we need dynamic range? Well, the best you can do with pulse counting is about 1 megahertz, and that's the transit time of the electron through the silicon. Basically what happens is, if I have the instant electron produces electron hole plasma, the electron hole plasma screens, and you can't pull it out with applying a big enough bias. So a megahertz count rate is 0.16 picoamps as a current. So if you have a counting detector and you did everything right, you probably wouldn't be able to deal with more than 0.16 picoamps in the incident beam. And a typical beam current is more like 100 picoamps. Now you can spread it over multiple pixels, but you're not getting very far. So here is the performance curve for a pulse counting detector. This is the Medipix, which is a fast pulse counter. And it basically drops off and misbehaves and get these volcano-looking images when you get above about a megahertz count rate. If you go into super resolution mode or charge summing mode, where you do sub-pixel localization, now your count rate drops even further, because now you can only have one electron every 4 pixels or one every electron every 9 pixels. So at high count rates, you're never going to use the super resolution mode because you just don't, you can't count fast enough. The other one is the detector goes nonlinear, not at this peak value of the megahertz value is over here, by the way. The nonlinearity is at about 10% of that level, so it's down about there. So if I want a linear detector and I'm doing pulse counting, I can't have more than 0.016 picoamps per pixel. And that's a very low number of counts. This is in picoamps per pixel. This is in 1 millisecond. This would correspond to 1,000 electrons there, and you're safe up to about 100 electrons. The K2 is sort of down about here because it's 25 electrons, but it has so many pixels you can just add pixels next to each other, and then it kind of brings it up and looks comparable to this thing again. Our detector, the pixel array detector you're going to work with, lets us handle beam currents of several picoamps per pixel, and then the number of picoamps depends on what beam voltage you're at. So it's pretty robust, it's pretty linear, it has a very high dynamic range, and then the reason of that high dynamic range was what let me go back and do this, that I can take my whole diffraction pattern and not saturate and dump a huge amount of beam current on, so I can record things quickly that otherwise you'd have enormous trouble doing, right? If this is what you're working with, there's not a lot of data processing you can do with this. All you can do is sum it up, basically. And here we are, central beam, not saturated, scattering from a single layer of atoms, and it looks pretty good. So how did the detector work? I can't do pulse counting because I can't count fast enough. So the design is a little clever. This is Sol Gruner's idea. What he does is he dumps charge into a big bucket. So we just simply collect the charge into a big capacitor and think of it as a giant bucket. And then what he does is he comes in with a scoop and scoops out 20 electrons at a time. And as long as he scoops out the electrons faster than they pour into the bucket, it'll never saturate. So all we have to do is we have to make sure that we have a big enough scoop to handle the charge coming in. And that's just a design choice. It's basically how big do you want your capacitor to be. And then you just count how many scoops you have when you fill up by an amount of the scoop. So we just run an 18-bit counter, and then that 18-bit counter says, I got an 18 bits, by the way, is like, many hundreds of thousands of counts. And each of those counts might be, say, buckets, little scoops of 20 electrons each. And then we just keep counting those scoops. At the end of the cycle, we read out the counter and we digitize the remainder. So at the end of the cycle, we look at what's left in the bucket, and that we can digitize very, very quickly. And that gives us 12 bits on this remainder, 18 bits on the counter, 30-bit dynamic range. That's about, it's a huge number. We use about 9 bits for 1 electron. So the dynamic range is about 1,000,000 to 1. I can record 1 electron, I can record 1,000,000 electrons, and the counter can handle it. So here we are just slowly integrating up, and this is what we measure on the remainder. And then here is the little counter adding up little quanta in units of multiple electrons. Put them together, and the signal is perfectly linear over a very, very large range. So this is a nice sanity check that we're perfectly linear over our 30 bits of dynamic range. And so the result is it takes a lot of work to saturate the detector. You can do it, but for most imaging modes, you won't need to do that. And so the detector is, you don't have to worry about a beam stop, and I can record every single electron that hits the detector. So you'll see this on the microscope. It's very compact. The sensor itself is about 2 centimeters by 2 centimeters in size. It has its own control electronics, so we can plug it on any microscope we like. And then it has its own data acquisition PC that you're going to play with this afternoon. Because I recorded the entire diffraction pattern, every single imaging mode that you would want to do, we can do simultaneously because it's all in the data set. And you can put them all on the same scale, and they're absolutely quantitative. So I think for the NC State guys, you guys love doing quantitative STEM, and you always want to know I over I0. Here it is. It's all measured for you. So much easier than calibrating your detector. And every imaging mode you can think of with every acronym available is available to you at atomic resolution. Here's a mode that pulls up the oxygen atoms very nicely and robustly. The thing we're going to do with the detector that's a little different from traditional diffraction work is we're going to measure probability currents. So remember I told you that the diffraction plane is the momentum plane. This is the definition of the expectation value of momentum. Wave function, momentum operator, wave function. Because I'm measuring it in the momentum plane, the operator commutes, and therefore I take the square of the wave function, which is the diffraction pattern, multiply it by the momentum operator, which is the pixel value, and the center of mass of my diffraction pattern is the average momentum transfer. If you rearrange this integral, write it out in real space, you'll recognize this as remember, P is minus IH bar del. So my momentum operator, rewritten in real space, is just this thing here. Quantum mechanics people, what is this operator? Probability current, right? So the center of mass of my diffraction pattern on the detector is the probability current flow. It's measuring how electrons are flowing from one place to another. The net momentum transfer from Ehrenfest's theorem, expectation value of momentum, time evolution of that operator is the commutator of the Hamiltonian with the momentum operator. And if I put it in for an electrostatic object, it's QE plus V cross B, which is the Lorentz force. Right? So now, the time evolution of the operator, which is the evolution with thickness, is just the Lorentz force on the electron beam from the sample. So it's measuring the electric field of the sample and the magnetic field of the sample. It's a great detector. You can also write this down in the strong phase approximation, which is what we talked about for the multi-slice this morning. Electric field is the gradient of the potential. So if you ask, when I take this expectation value, what do I get from my momentum operator? I get a convolution of the square of the probe wave function with the momentum operator. This is good because this is an incoherent imaging mode. And so I don't have to worry about Fresnel contrast and all those coherent artifacts. So what I'm going to measure with the center of mass image is the gradient of the potential, which is the electric field. There's a cheap and dirty way to measure center of mass, and that's to look at the deflection of the electron on the detector. This is called differential phase contrast. If you do left minus right or up minus down, it gives you an approximation to the center of mass. It's not a great approximation, but if you can't afford a pixel array detector, this is the trick you can use. Okay, so I told you that the momentum transfer is the Lorentz force. So if I put an electron through a magnetic field, the beam is deflected. The scale of these deflections is on the order of microradians for a typical magnetic sample. And a typical electrostatic angle is more like milliradians. So magnetic fields are hard to see in the presence of electric fields. Typically what we're going to do is we either make a very parallel beam and we try to average over the grain structure, or we need a smart detector. So here we are just looking at the deflection of the electron beam in a cobalt film. You'll get to play with this data set this afternoon. These are the magnetic ripples in cobalt. And you can put it all on a quantitative scale because you have the full diffraction pattern. So we know what the B field is. So that's the good news. The bad news is, remember the first time I used center of mass, it was not to measure magnetic field, it was to look at grain contrast. So here's a ferroelectric sample of bismuth ferrite. And look at the beautiful contrast in the bismuth ferrite grains. So a lot of people are like, hey, I've seen electric fields. There's a particular group from Japan that consistently gets this wrong and have published papers, one recently and a couple before, where everything they've done is just wrong, but they're very good at making the naive mistakes. So in this case, they had looked at a ferroelectric and thought they had domains in lead titanate. The clue that this is not domains in lead titanate is look at the strontium ruthenate underneath. It also has grain contrast. Strontium ruthenate's a metal. It's not a ferroelectric. This can't be an electric field. It's just simply the tilt of the Avold sphere. So with the pixel array detector, what we do is we look at the Kikuchi bands, and we measure the shift of the Kikuchi bands, and we plot out the tilt in milliradians. And here's the physical tilt of the crystal, which is basically the crystal went tetragonal and tilted. So in this case, the center of mass signal is not electric field, it's not magnetic field, it's crystal tilt. The nice thing about the pixel array detector is you can separate out these effects, because I can measure the tilt and then correct for it. This is what would have happened if I'd just looked at the center of mass. In the interest of time, I'm going to skip this. How are we doing for time, Lena?
5 minutes.
Okay. So very quickly, if I have a diffraction pattern and I put it in a very slowly varying electric field, then the potential V of R is E times X. If you Fourier transform a ramp function, it leads to a shift in diffraction space. So long-range potentials, slowly varying potentials like for magnetic fields, all they do is they shift the diffraction pattern. Mathematically, that's the proof over there. So that's why these center of mass signals are good at looking at electric fields and magnetic fields. The slowly varying part is just a shift of the field. If I look at a diffraction pattern from a single atom, and then Michael has calculated this, what I get is little fringes and intensity changes across the disk. The disk doesn't shift. So a delta function potential gives me contrast inside the disk, but no shift of the disk. So now I have a way to separate out short-range electric fields from atoms and long-range electric fields from long-range magnetic fields. So this is just quickly showing you a diffraction pattern. Over here, the beam is not on an atom, and there's just mostly the central beam and not a lot of scattering. If I'm on the tungsten atom, there's a lot of scattering. If I integrate up this contrast, this would give me the annular dark field signal, right? More counts on the atom, less counts off the atom. If I zoom up very closely and ask what does my diffraction pattern look like inside the disk, on an atom and off the atom, over here I'm just to the side of an atom, and you can see that there's a contrast change across the disk. The way you interpret this is as a probability current flow. There are more electrons going towards the atom than there are electrons going away from the atom, right? The atom is positively charged. It's pulling electrons towards it. If I go to the other side of the atom, I can tell where I put the beam because there are more electrons flowing towards the atom column than away from the atom column. So that's what's nice about thinking of this as a probability current flow, is I look at my map, I can tell you where the electrons are going. And then if I'm on the atom, it's reasonably uniform. OK, so small things cause shifts inside the disk. Large things shift the disk itself. So if I now take my center of mass image and I break it up as a function of angle, what I see is right near the edge of the disk, I have the contrast looks a bit messy. But if I take the edge of the disk minus the middle of the disk, so this is just a ring around the edge of the disk, then I get contrast just from the shift of the disk, and I see some nice ripples. If I take a look at the contrast at large angle scattering and I look at the center of mass, then I'm going to get the shift of the Avold sphere, and I'm going to get grain contrast. Put that. So those features are probably about 20 nanometers. Yeah, so always have a scale bar. I'm looking for my offending student.
Right. Blame it on them, David.
Yeah, but she put a scale bar on this one. So here it is. If you do center of mass from a region that's sensitive to the edge of the disk, you'll pick up the magnetic ripples in the sample. And if you pick up the piece where you've just looking at the Ewald sphere tilt, you'll pick up the grains. So now you have a measurement simultaneously of grain contrast and tilt. And if you tried it by the conventional methods, it would have failed. So I'm running out of time. I'm going to talk about this stuff in more detail at the workshop. But if you have the full diffraction pattern, you can phase it, and you can solve and improve the resolution of the microscope well beyond the diffraction limit of the instrument. So over here is the angular dark field image, which is running at twice the cutoff angle of the aperture because it's the square of the wave function. And then here is some early data where we've pushed out our information limit to 4 times the aperture size. So you can see by doing full diffraction information at every point at atomic resolution, the image looks much, much nicer and is much higher resolution and higher contrast than angular dark field imaging. And I'll talk about that on Saturday. Yeah, okay, and then we're showing off because now we're below half an angstrom. Okay, so other things you can do with the detector. Because I have a diffraction pattern at every point, we can measure the shift of the diffraction pattern, and then you can measure strain and lattice constant very precisely. And the shifts that you can measure are really tiny, 0.3 picometers. You can measure rotations to, is that degrees or radians? Radians, okay. So that's ridiculously, it's really, you know, so that's 10 milliradian tilt. It's pretty tiny. I think in the interest of time, I should stop over there. The two things I want you to remember. First is from the detectors. If I have n counts on the detector, what's the noise? Square root of n. Great. So if you've only got, you know, if you've only got 4 counts in the channel, I've got 50% noise in my image. You're not going to be happy. So that's a big problem for X-ray mapping. Then the second thing is the pixel array detector lets me get a full measurement of momentum space at every position in real space. That's a phase space measurement. It's a 4-dimensional data set. 4-dimensional data sets are very hard to look at. So this afternoon, you're going to learn how to use a 4-dimensional data viewer system.